Hello and good day, everyone. I am Gian Gonzales from the University of the Philippines, Diliman. I am here to present our work with the title Voice Conversion of Philippine Spoken Languages Using Deep Neural Networks. For this presentation, I'll start with the introduction of voice conversion and its applications, then the already implemented voice conversion systems in literature. Next is our research methodology, followed by the results and analysis, and finally, the conclusion. Voice conversion is the process of converting a source speaker's voice into the target speaker's voice without changing the linguistic information. These systems have a lot of applications such as spoofing or identity protection, speech signal restoration, speech data augmentation, and vocoders, which can be used for text-to-speech and music applications. Here are the parts of a voice conversion system. There are two phases in which the system undergoes. First is the training phase. The inputs are parallel data of source and target speaker audio files. The first process is the feature extraction method, where the speaker characteristics are mathematically modeled. These features will then be fed to the VC model for learning, and the output will be a trained model which contains the transformation function. Second is the testing phase. You just need to have the source speaker and the trained model. The source speaker undergoes the same feature extraction, then these features will be fed to the decoder together with the trained model, and the output will be the converted target speaker. There are two ways to test the performance of a VC system. First is using objective metrics, such as the Melkepstral distortion, or MCD, which is also called as the Kepstral distance, and the fundamental frequency root mean square error, or F0 RMSE. The converted or synthesized outputs are tested against the target or expected outputs using the following formulas. The ideal score for both tests is 0 or near 0, which means perfect similarity. The second way for a system evaluation is using subjective metrics. The mean opinion score, or MOS, is where the listener ranks the sample from 1 to 5 in terms of intelligibility and naturalness. Another is the ABX similarity test, wherein the listener is tasked to determine whether the test sample X is from the source or target set. Shown here are different voice conversion systems implemented in literature. One of the earliest works is from Abe et al., which is voice conversion through vector quantization and the use of histograms for codebooks. They achieve an ABX scores of 56.8 to 64.6. Next is from Kim et al., which uses hidden Markov model, or HMMs, with 3.3 to 3.4 MOS scores and around 3 dB of Kepstral distance. Stiliano et al. Developed a system using Gaussian mixture models, or GMMs, which achieve -6 to -2 dB for Kepstral distance and non-standardized MOS scores of 5 to 7 on a scale of 1 to 10. On to more recent works, the work of Nirmal et al. Uses complex capstrum-based voice conversion using radial basis function, which achieve a high MOS scores of 4.07 to 4.64. One work of Ye et al. Uses deep neural networks as the VC model, which achieve 3.4 to 3.9 MOS and 0.89 in Kepstral distance. As you have seen, most of the voice conversion systems available have focused on the spectral parameter of the speech, such as the spectral envelope and the cepstral parameters. In Ming et al.'s research of fundamental frequency modeling using wavelets for emotional voice conversion, they hypothesized that prosodic features such as the F-naught contour and its transforms, such as the continuous wavelet transform, may be used to enhance the voice conversion process. Now, in our paper, the research objectives are as follows. We aim to implement a DNN-based voice conversion system that includes the continuous wavelet transform of F-naught, and to test that system using objective and subjective metrics. We also aim to apply the voice conversion system for Filipino languages, such as Tagalog, Cebuano, and Hiligaynon. Shown here is the methodology. We retain the deep neural network as the VC model from Ye et al.'s work, and the proposed feature extraction is inspired by Ming et al.'s work. For our data gathering and preparation, we had 4 different languages. The Tagalog, Cebuano, and Hiligaynon were derived from the ECIP and FSC project database of our laboratory. The English is derived from the CMU Arctic database. For the training data, there are 50 utterances per speaker. 4 speakers per language, 2 male and 2 female, with an average of 3 minutes and 38 seconds per speaker. For the testing data, there are 10 utterances per speaker, which is roughly 34 seconds each. Our proposed feature extraction contains 3 different features. First is a spectral envelope modeled using 60-dimensional cepstral coefficients. Second is the banda periodicities, and third is the F-naught contour. All 3 are extracted using the world vocoder. Finally, as inspired by Ming et al.'s work, the F-naught contour is further decomposed via continuous wavelet transform using the Mexican hat mother wavelet. For the deep neural network, we use 6-layer DNN with 1024 units per hidden layer, hyperbolic tangent as activation function, exponential learning rate decay, and the training phase has a maximum of 50 epochs. We trained 16 different DNN models, 16 pairs, 4 pairs for each language, male to male, male to female, female to male, and female to female. All are done using the Merlin toolkit. On to the results and discussion. For the objective metrics per language, Hiligaynon has the least MCD score of 5.5335 dB, and English with the least F-naught RMSE of 20.2535 Hz. For the pairwise objective metrics results, female-to-female conversion has the least MCD of 5.4425 dB, and male-to-male conversion has the least F-naught RMSE of 19.8585 Hz. As you have noticed, the two metrics, MCD and F-naught RMSE, are not always consistent with each other. As for the subjective metrics per language, you have the highest MOS naturalness score of 2.7167 for English and intelligibility score of 3.0875 for Cebuano. As for the subjective pairwise conversion results, both the highest MOS score for naturalness and intelligibility are from the female-to-female conversion. In conclusion, this project has implemented a voice conversion system for English, Tagalog, Cebuano, and Hiligaynon. The results show that good objective results does not necessarily reflect to the subjective preferences. Furthermore, The two objective metrics, MCD and F0 RMSE, are not always consistent with each other. Here are some conversion samples. For the English language source speaker,
God bless 'em, I hope I'll go on seeing them forever.
and the converted output,
God bless them. I hope I'll go on seeing them forever.
for Cebuano female source,
Daghang salamat.
and the converted male output,
Daghang salamat.
for Hiligaynon male source,
Malipayon nga panamyaw.
and the male synthesized output.
Malipayon nga panamyaw.
Lastly, for the Tagalog female source,
Magandang tanghali po.
and the female synthesized output.
Magandang tanghali po.
Before I end my presentation, I would like to acknowledge the following. My co-authors, Sir Cristron Rudolph G. Lucas, MSEE, Sir Michael Gringo Angelo R. Bayona, MSEE, Dr. Franz A. De Leon, PhD, and lastly, the UP Digital Signal Processing Laboratory. Thank you all for listening. That will be all, and have a good day.